Hello dear students, I hope all of you are doing fine. In this video also we will proceed with the numerical calculation. Let us see what is this numerical asking us to calculate. The standard electrode potential for Daniel cell is given as 1.1 volt. Calculate the standard Gibbs energy for the reaction. The reaction is mentioned. We have to calculate the Gibbs energy for this very reaction. The first step is to write down the reaction and to denote which is anode and which is cathode. Anode means oxidation, cathode means reduction. That means Zn converting to Zn2 plus is oxidation, oxidation number is increasing. Cu2 plus converting to Cu is reduction, that means oxidation number is decreasing. So anode, cathode. N is the number of electrons participating in this reaction. So how many electrons are participating? 1 electron is participating. Zn is losing 1 electron, giving it to Cu. By now I think it is clear enough how the electron transfer takes place. Now F, Faraday. Faraday value, either you can take 96500 or 96487. You will get the same answer. Now anode cell value is already mentioned, which is 1.1 volt. Now let us search the standard Gibbs energy. We know that standard Gibbs energy is given as del R G naught minus NF E naught cell. This is a formula used for the calculation of standard Gibbs energy. Now what is N? N is the number of electrons participating in the reaction. We know it is 2. Faraday's 96487 Coulomb mole inverse. You can either take 96500 into what is E naught cell? E naught cell is 1.1 volt. Now upon calculation we'll get 212271.4 joules mole inverse. Now this joules, if we have to convert to kilojoules, that means 1 kilo is equal to 1000. So 1000 has 3 zeros. If we are to convert it into kilojoules, what we will do is we will move the decimal point to 3 points. That means it will be 212.27 kilojoules mole inverse. So this is how we are going to calculate the Gibbs energy for the reaction given. Kilojoule mole inverse is the unit of Gibbs free energy change. Let us try to calculate one more EMF numerical. Calculate the EMF of the cell in which the following reaction takes place. Reaction is given, the concentration of the electrolyte is given, E naught cell value is also given. This reaction, if you see, it is already a balanced reaction. So when you do at anode, at cathode, you will get the same reaction. Sometimes when only the cell is mentioned, that time you have to do at anode, at cathode. But if you see the reaction is already balanced, even if you don't do this portion, it's fine. So let us try to do the calculation. We have to calculate the EMF of the cell. E cell, we will write down this formula which we already know. Log concentration of the product, concentration of the reactant. Now E naught cell value is already given. Upon division, we will get 0.029 log. Now Ni2 plus value is also given. That means the concentration is given. We have to write the concentration. Ni2 plus, the concentration is 0.160. 0 has no value after point, so we can directly write 0.16. 0.16, and we already know by now that the concentration of metal in solid form is already 1, so Ag and Ni will be 1, so we will not be writing. Now Ag plus, the concentration is also given, that is 0.002. So 0.002 and the coefficient is 2. Now here, this very number upon simplification, 0.16. If we want to remove the decimal point, what we will do is 16 divided by point will be converted to 1. And how many numbers are there after the point? 2 numbers, that means 2 zeros. So this one can be written in this form 16. Since this is in denominator, when it goes to the numerator, it will be inverse. That means how many zeros? 10 to the power minus 2. Similarly, 0.002 whole square. Upon squaring it, we will get 0.000004. So this, if you want to remove the decimal, what we will do is divide by, point will convert to 1 and remaining numbers will all become 0. Now how many zeros are there? 6 0. Since it is in the denominator, when it goes to the numerator, it will be 10 to the power minus 6. So upon simplification, what we are getting? 16 into 10 to the power minus 2 and 4 into 10 to the power minus 6. Now let us do our calculation. That is 1.05 minus 0.029 log. This one we got as 16 into 10 to the power minus 2, 4 into 10 to the power minus 6. Now here 4 4s are 16. We can do in this manner. So 1.05 minus 0.029 log. Now we have 4 into this 10 to the power minus 6. If it goes to the numerator, it will be converted to positive. That means it will be 10 to the power plus 6. So it will be in this manner 10 to the power minus 2 into 10 to the power 6. Into means power term will be added plus 6. So we will get 10 to the power 4. So 10 to the power 4. Now if we try to open the bracket, what we will get is log 4 if you remember, log A into B is log A plus log B. Now here this is A, this is B. So what we can write here is log A plus log B. This is all coming from the formula. So you have to always remember the formulas. So 1.05 minus 0.29. Log 4. What is log B? 10 to the power 4. 10 to the power 4, this type we have already done. That means it will be 4 log 10 minus 0.029 log 4 value is 0.6 plus 4 log 10 value is 1. So here upon multiplication, what we will get is 4.6. So here it will be written in this manner. If we multiply, we will get 0.133, and upon subtraction we will get 0.917. So this is the EMF of the cell. So in this manner you are going to calculate. You have to remember the log value and how you are going to convert log into their respective numbers. Let us see the next numerical. It's your in-text question 3.6. The cell in which the following reaction occurs, the reaction is given, has E0 cell, that means the standard cell has been given, that is 0.236 volt at 298 Kelvin. Calculate the standard Gibbs energy and the equilibrium constant of the cell reaction. We have already done one numerical with Gibbs energy, but here we will also be doing equilibrium constant. So for the given reaction, we have to know how many electrons have taken part in the reaction. But here, how will you know how many electrons have taken part in the reaction? We will see the least number of charge. That means, For iron, here it is 3 plus, but in the product side it is 2 plus, and here iodine has 2 coefficient. That means 2 electrons have taken part in the reaction. So N is written as 2 because 2 electrons have taken part in the reaction. And for Gibbs energy, the formula is given in this way. And we already know it is 2. Faraday's value we know. E naught value is also given in the question. So upon putting all the values, we will get minus 45.54 kilojoule mole inverse. This is a unit of Gibbs energy. Now we are done with Gibbs energy calculation. Now the question also asks us to calculate equilibrium constant. So at equilibrium constant, we know the formula is given in this way. Gibbs energy is equal to minus 2.303 RT log Kc. Log Kc is the equilibrium constant. So we have to find log Kc. So upon bringing log Kc to the left hand side, we will get this very equation. So now, Gibbs energy we have already calculated, which is minus 54. Here there is minus sign as well. So from the calculation we already got one minus sign. So minus 2.303. Gas constant value is given as 8.314 into 10 to the power minus 3. Temperature is given as 298 Kelvin. So from this, upon calculation, you will get 0.00798 into 10 to the power 3. So when we move the decimal point to the right hand side, that means, okay, let's do the long card. That means if we want to remove this decimal point, what we do is, this point is written as 1, and after point, how many steps we want to move ahead? 1, 2, 3. 3 steps we want to move. That means 1, 2, 3. So what we get here? 7.98 into 10 to the power 3. So how many zeros are there? 3 zeros. So what can be written? 10 to the power 3. Now when it goes to the numerator, it can be written as 3 minus 3. So ultimately log Kc we get 3 minus 3 is 0. So we get 7.98. So from the calculation we got log Kc value as 7.98. Now we have to find Kc, equilibrium constant. So 7.98, this log goes to the denominator. Don't write in this manner, but it is just for explanation. Now since it is in the denominator, when it goes to the numerator, what it will be? Log inverse. What is log inverse? Log inverse is anti-log. So Kc is equal to anti-log of 7.98. Again, I'm repeating, don't do this step. This is just for explanation. Directly write the anti-log. So Kc is equal to anti-log. If you have done the calculation, the one page which I gave for anti-log calculation, you'll be able to do this. How do we do the anti-log? 7.98. We will separate this from the decimal. From the decimal means 7 plus. This very 7.98 can also be written as 7 plus 0.98. Now 7 plus 0.98 will be 7.98. So it is the same. So this can also be written as 7 plus 0.98. Now Kc is equal to anti-log. Now our next step is to put log. Log 10 to the power 7 plus log 9. Why did we write log 9? Because 0.98, we have to write that log which has the closest value to 0.98. So log 8 value is 0.9, log 9 is 0.95, log 10 is 1. Which will be the closest value to 0.98? It will be log 9. So when we are doing anti-log, the first value given we will put as log 10, whatever the value is, plus we will search the closest value in the log table and we will write the log. So in this case it is log 9. So our next step will be Kc is equal to Kc will be equal to anti-log. Now this, it is in the form of log A plus log B. Now log A plus log B is written as log A into B. So this very thing can be written in the form of log A into B. So what we will write is log, this is taken as A, this is taken as B, log A into B. Now anti-log and log will get cancelled. So your Kc, what you are getting is 9 into 10 to the power 7. So this is your final answer. So equilibrium constant we got as Kc is equal to 9 into 10 to the power 7. You keep on practicing. With practice, all these things will become familiar, so it will become easy.